Hi, I'd like to talk about an example of applying Newton's second law for an object that is traveling in a circle. So, say you're driving a car along a flat desert road that makes a 180-degree turn with a radius of 75 meters. And you want to figure out the maximum possible speed that you could negotiate that turn. Well, in order to be able to turn in the first place, we need a force that'll change direction with the motion of your car. So, if we look at the forces, well, on Earth or any planet, we would have a weight pointed straight down. If the road is flat, we'd have a normal force pointed straight up. And if we're heading out of the board here, looping around into the board, then the direction of our acceleration would need to be to the right initially. And we do have a force anytime we have a surface with contact parallel to that surface of contact. And that force is the force of friction. And because our motion is centripetal, center seeking in towards the center, that means our force of friction has to be in towards the center. Now, if you travel too fast, your car will slide. And if your car slides, it always slides to the outside of the turn. That's because if your car is sliding along the ground, you have kinetic friction, and if your car is sliding to the outside of the turn, your car would be sliding to the left, the force of friction would be to the right, and you would end up crashed into the ditch over here. So I'm just going to draw in a cartoon cactus to say that's probably not where we want to be. So the force that we need in order to make this happen and not crash is a force of static friction. Now it sounds weird saying static friction because, well, isn't the car moving? The idea is the car is moving, but if you were to take a look at how the tire hits the road, the patch of tire that is in contact with the road is going to be at rest relative to the road. And we'll talk more about the idea of rolling without slipping as we get into talking about chapter 10 with rotational motion and combined forward motion and rotational motion. So the other way to think about it is if you've ever been stopped at a light, get a little sort of excited, hit the gas harder than you plan, your tires start spinning. Well, when your tires are spinning, you accelerate forward, but much, much, much less than if the tires stay locked in place relative to the pavement. And that's why with anti-skid technology, you can get better acceleration in a car. So, we've determined that we have static friction. Static friction is as large as it needs to be. So that means we actually can create a limit, a maximum possible speed where we get a maximum possible force. So if we look at our forces in the y direction, all we can say is that our normal force is going to equal the weight. And the weight is just the mass times the strength of gravity, as long as we can ignore effects like aerodynamics. Now in high performance cars, you want to have a wing that has a down force rather than lift, because if you push down on the car more than gravity pulls down on it, you get more normal force, which means you can go faster. Which is basically why F1 race cars look like they have giant wings on them, because they do. It's just they have negative lift rather than positive lift. So, here, no lift, no wings, nothing. Normal force is the weight. In the direction of the turn, well, that's our centripetal force. It's uncanceled. So that force that's turning us is our static friction. And at a maximum, the amount of static friction is equal to the coefficient of static friction times our normal force. So, for centripetal force, the size of the force is the mass times our speed squared divided by the radius. Our radius is fixed, and we want to calculate our maximum possible speed. That's going to have to equal the coefficient of static friction times the mass times the local strength of gravity. Well, mass cancels out of this problem. And you probably notice in physics, mass cancels out a lot. Well, after I've done that cancellation, the speed squared over the radius is the coefficient of friction times gravity. So if I multiply both sides by my radius and then take the square root, my maximum speed has a size equal to the square root of the coefficient of friction, the strength of gravity, and the radius of the turn. So in my picture, I drew a radius of 75 meters. Now, we would need a coefficient of static friction. And one of the things about coefficients of friction is they can vary wildly as conditions vary wildly. So if you have different types of tire rubber, you're going to get very different coefficients of friction. Super high performance racing tires can have coefficients of friction of 2 to 4 or even higher. The downside is the higher the coefficient of friction is, the faster the tire wears out. So racing tires, things that are really designed to grip the road, might have a coefficient of friction greater than 1. So since from context this looks kind of like the old-timey Batmobile from the 1965 Batman, which is what I was going for in the picture, let's say it's a high-performance tire with a coefficient of friction of 1.5. So that means that Batman can drive around the 75-meter radius turn at, so I multiply 1.5 times 9.8 meters per second squared times 75 meters. The square root of that gives me 33.2 meters per second, which in miles per hour works out to be about 74 miles per hour. Now, an everyday car, again, conditions change. If you're out in the desert and there's a wind, there might be sand. Sand on the road is going to lower the coefficient of friction. So if you try driving 75 miles an hour around this turn, or even 70 miles an hour around this turn, if you hit a patch of sand, you're crashed off to the side of the road. Because you start sliding because there isn't enough static friction to keep you making that turn. If the road's wet, if there's oil on the road, if you have a normal passenger tire usually has a coefficient of static friction on dry pavement, which again, it depends. Are we talking concrete? Are we talking asphalt? Are we talking tar? Are we talking macadam? Are we talking tarmac? All of those different permutations of what we make a road changes the coefficient of friction. Typically, though, we're looking somewhere usually between 0.6 to 0.8 when it's dry. You get it wet, you get it oily, then we're talking 0.2 or less, particularly if it's icy. It can be smaller than 0.1. So in icy driving, as we have winter coming up as I'm recording this, slow down. The speed that you have going into a turn is the one thing you can control. So the slower the speed, the less friction you need in order to turn. Stay safe, and thanks for watching.